Okay. So, coming to the continuous joint probability, there are certain things, again, notation which we need to know. Discrete is summation, continuous is integration, as all of you know. But then definitions, if you know properly, then problems would be a left-hand job for you. Okay. The distribution function of a two-dimensional random variable capital X comma capital Y is a real valued function capital F. Usually, guys, there's one thing which you ought to remember, that is usually F, capital F or small f, these two are used for continuous random variables. And then capital P and small p are used for discrete random variables. Okay, that's the notation. Usually the standard book Gupta and Kapoor uses. Many of the foreign authors as well use this. Foreign authors usually directly they use capital or small f, and directly they use small p or capital P, which means that one is discrete, the other is continuous. Okay, but Gupta and Kapoor definitely says that f's are used for continuous, and usually right, functions we integrate. Okay, functions we integrate. So f for function, so integrate. P is a probability, which would be a number, so can be discrete as well. Okay. Now, the distribution function for a two-dimensional random variable, how is it defined? You can just see. It is notated by capital F, suffix X, capital Y of small x and small y. This is equal to probability of capital X less than or equal to small x, capital Y less than or equal to small y. Okay. Yeah. Coming to the properties of joint probability distributions, there's one property of this. Proof is very simple, guys. It has its origins from the set theory and the distribution of union over intersection kind of things, which is very simple. I'll try to make the proof of it as well, but then proof is not very much useful for engineering students. But then there's this property that you ought to remember, that is probability of A less than capital X less than or equal to B, A1 less than, okay. And then A2 less than Y less than or equal to capital B2 less than or equal to B2. That value is equal to capital F of X comma Y, B1, B2, capital F of X comma Y, A1, A2. Both are added, but then the thing that is subtracted is the combination of A1 with B2 and B1 with A2. Capital XY, I mean the cross variation kind, usually we call that to be cross variation. Capital FXY with A1, B2 and XY with B1, A2. You can just see B2 is included, A1 is not included. B1 is included, A2 is not included. So that is subtracted. Okay. The proof is very actually simple and trivial. Okay. I shall do it probably if possible in the coming videos to go. But as of now, I just want to show this property to you. Coming to the second property, as we have seen in discrete random variables in one dimension, f of minus infinity is defined to be 0, f of plus infinity is defined to be 1, capital F. Okay. Similarly here also, minus infinity of comma y and x comma minus infinity are defined to be 0. F of plus infinity comma plus infinity is defined to be 1. These are basically like assumptions or properties which removes the hurdles when we are doing problems on this. Okay, yeah. The density function of small f of x comma y is if it is continuous, then we can see this third property, that is dou square capital F by dou x dou y of all the derivatives. If the function is continuous, then all the derivatives will exist. So the second derivative of capital X with respect to x and y would give me the small f of x comma y. I hope you remember in one dimension df by dx would be small f of x. Okay, similar to that. It's an extension of it. Then here you go with again cross variation, the double derivative with respect to x and y. Okay. Apart from these things, apart from these things, how do I define marginal distributions? Marginal distributions for continuous and discrete. Of course, already we have seen for discrete in the previous video. I'll just write marginal distributions or marginal distribution of x. Of course, I can write it for you in discrete as well. P capital X, and just to show the difference, just to p x comma y. Okay. And here it would be minus infinity to plus infinity. Small f x y dy. Okay. Yeah, y is varying. In the above also, y is varying. This is for discrete and this is for continuous. Yeah, okay. And then you can see here the clear difference. F is used for the functions, I mean, which are we are integrating. P is used for just the numerical values, the probabilities. Okay. Similarly, I just write the marginal distribution for capital F capital Y as well, where Y is fixed and X is varying. That is shown as well in this notation in the summation. And then here minus infinite to plus infinite, F capital X Y, X comma Y, it would be dx for continuous. You can as well check for this marginal density functions, F capital X of this is nothing but d capital X, F of X. Actually, for engineering students, these are least used. Some questions can be asked in GATE, but otherwise in the classroom problems and in the exam problems for the engineers, I don't think you will get any problems on these things. But anyways, just for your information, probably if someone is going to give GATE in future, they'll be useful to you. Okay, derivative of this fx and fy. Fx with respect to dx, fy with respect to dy. Minus infinite to plus infinite. F capital X capital Y. Yes. This is how we'll find the marginal density functions. Okay. Now, like how we do the same thing in one dimension, in derivative of capital F. Here it is suffix x and suffix y. When both are there, I have shown you the partial second order derivative. Okay, with respect to x and y. I'll stop the video here.